Welcome to Easy BTech, your guide for BTech and beyond. In the today's lecture, we will discuss about FET constructions, how the FET is constructed, and how the operation of FET we will see today. Okay, students, very important topic. FET. Today we know this is field effect transistor. Field effect transistor. Okay, students. Construction of n-channel Jfet. Construction of n-channel Jfet. N-channel means we can clearly see this terminal is a source, this terminal is a gate, this terminal is a drain, these are the P plus layer, P plus, this is channel, it is an N channel, N channel. Okay students, now this terminal we call as a gate, this terminal we call as a gate, a highly doped or a heavily doped P plus a heavily doped P plus type material is placed in a N channel to create a gate terminal, and it is backsidely connected. This is also a gate terminal. It is a gate terminal. It is also a gate terminal. It is a gate terminal and it is a gate terminal. Okay students, now you can see this is source, this is drain. How many terminals of n-channel Jfet? We have three terminals: source, drain, gate. Okay, from this diagram we can represent as source. This terminal is connected. This terminal is connected to the negative n-type channel. Either one end with a negative potential, Next, the electrons in the channel flows from source to drain. Remember, the flow of charge carriers always from source to drain. Okay, next it is a source terminal. Next terminal is drain. See here, this is a source. Source is connected to the N channel. Within an N channel, the source is connected to one end. It is an other end. Okay, drain. This terminal, this terminal is connected. This terminal is connected to the negative N type channel, negative N type channel in the other end, in the other end, the other end with a positive potential, with a positive potential. Now you can remember the students. Students, you have to remember the point here. When you apply a voltage between source to drain or drain to source, then only the charges can be moved from, okay, then only the charges can move from source to drain. Okay, now current flows from drain to source, drain to source. That is why we will call the current IDS. Okay, or simply we will call minus of ISD. IDS is the current through the drain to source in an FET. Is it clear? Electrons are moving in this direction. Current will be moving in this direction, opposite to the direction. It is a electron and it is a current in their movement. Is it clear? Next. This is about a source material and this is about a drain material. Next. Gate. 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 A heavily doped p-type, a heavily doped p-type silicon is placed on top and bottom of the channel, bottom of the channel, bottom of the channel. Is it clear? Now you can see in this diagram. Now it is a channel. Within the channel and the top and the bottom we are keeping with a P plus layer. Okay, a heavily doped p-type silicon is placed on the top and bottom of the channel is known as gate, is known as gate terminal. Okay, by which a PN junction is formed, PN junction or PN junction diode is formed. Okay, now you can see here. Here, now it is P material N type. Here it can be formed a one junction. Is it clear? Okay, students, this is about get up a channel. Next one is a channel. A channel is a negative or N-type semiconductor material. Semiconductor material. Either end of the channel, source and drain are depleted. Okay. The majority charge carriers the majority charge carried in the channel are electrons or electrons. Okay, students. Okay, we will see now symbolically. Symbolic representation. We generally represent like this. It is an N channel. Okay, this voltage is VGS. Always it is operated in reverse bias. And the voltage here to here, VDS, output voltage. It is a drain terminal. It is a gate. It is a source. This we will construct. This is a drain. This is a gate terminal. Okay, we can apply an input voltage between gate and source. Gate and source, we can apply input voltage, that is VGS. VGS, and the output voltage VDS. Okay, it is a channel. Okay, now you can see what happens to this operation. This is a construction, a basic construction. It is a representation, just construction of N channel Jfet. N channel Jfet. Now you can see when case 1, when VGS is 0 and VDS is 0. When VGS is 0, VDS is 0. Here no voltage, here no voltage, here no voltage. Then what happens? When VGS is 0, VDS is 0. Current flow through the channel is null. Jfet does not conduct. Jfet does not conduct. Okay, this is the case when current flow through the channel is null. Is it clear? Case 1, when VGS 0, VDS 0. Second case. Case 2, when VGS is 0 and VDS is plus 5 volts. This is a case. Second case. Now what you can say? Now you can see here we are not applying any voltage here. You are not applying any voltage across the VGS. Now you are applying this VDS voltage. Now all the negatives are moving this side. Okay. Now due to this n-type material, all the electrons are moving in this direction. Is it clear? Now this is called, we'll call it is a channel length. Okay, from here to here we'll call channel length. Now you can see when VGS is 0, maximum electron will flow. When case 2, when VGS is 0 and VDS is plus 5, maximum current flows through the channel. The transistor starts conduction. Current through transistor is maximum. Current through the transistor is maximum. That can be represented as IDSS. Drain saturated current. This we will call as a drain saturated current when VGS is 0, VDS is plus 5. Means a maximum when VDS is maximum. Okay. There is no change in the channel length. Length remains constant. Due to VGS is 0 volts. There is no change in the length. Then the current through the transistor is maximum. Next, case 3. When VGS is applying a negative voltage, VGS is minus 5 and VDS is 0. Then current flow through the transistor is null due to VDS is 0 volts. Due to VDS 0 volts, current through the transistor is null, 0 volts. No current flows because current in the transistor can flush due to the VDS voltage only. The charges from source to drain, movement can be takes place by applying the VDS voltage only. Is it clear? But the current flow through the transistor, can be reduced using or controlled by using the VGS voltage. Okay, that is why this input electrical field will decide the amount of current flow in the transistor. That is why it is known as a field effect transistor. The amount of the input field which is applied across the gate terminal, which decides the amount of current flow in the channel. That is known as a field effect transistor. Okay, now when VGS is maximum negative and VDS is 0, there is no current flow. Means you can see when VDS is maximum, overlapping can be takes place. Next. Case 4. When VGS is changing like -1, -2, -3, so on like this, and VDS is +5. Okay. Then the current flow through the transistor is changes gradually due to variation in the gate voltage, due to which FETs are known as voltage controlled device, voltage controlled current source, known as voltage controlled current source. Now you can see here clearly. Now when VGS is suppose -1 volt, when you are taking the VGS is -1 volt. Now due to this -1 volt, what happens? -1 volt, what happens? Here P is a P-type material and it is an N-type material. N is a P plus means heavily doped. N means lightly doped. Now always you can remember the width expansion or the depletion region, because here you can see VGS, negative is applied to the positive and positive is applied to the negative. Source is a negative, na? For negative you are applying a positive and for a positive you are applying a negative. Now it is a reverse bias. When this is in reverse bias, then what you can say? When it is applying a negative, here also you are applying a negative. Okay, here it is positive. Now this PN junction diode is operated in reverse bias. When it is operated in reverse bias, the width expansion plays very important role. That is, when VGS is less voltage, the width expansion, because of the P is heavily doped, width in the P material can be less. It means width expansion or depletion region expansion is inversely proportional to the doping concentration. Width expansion is inversely proportional to the doping concentration. Now suppose you can see this is a material, it is a P plus it is N. Now N is lightly doped, P is heavily doped. then the width in P side is this much, but in an N side this much. Is it clear? Now here the width is very narrow, but here the width is very wide. It means due to lightly doped width expansion, more takes place in the channel. Okay, width expansion is maximum, depletion region width expansion is maximum in the channel compared to the P-type material. That is why here the width expansion is like this, but whereas here it is like this. This is the total width expansion. Here also same. Now you can say, now if you see the length, now you can see this length. Now the length is reduced. This length is reduced. Now similarly, if VGS is increased, if VGS is increased by minus 2, now we can say when VGS is minus 1, VDS is plus 5 at that particular point. Now here negative given, the channels are flow within this gap only. Now as length is reduced, less amount of the charges can move from source to drain, then lesser amount of current produced. Now as VGS is increased more, then the width expansion like this and like this. The depletion region width increases. Now you can see the length is now very narrow. What is the length now? Only this is the length now. Now the length is this only. Very small length. All the charges due to this VDS voltage, all the charges are moved in this gap only. In this gap only, within this gap only, the charges can be moved. Okay. Now as VGS is increased further, now what happens? This depletion region width overlaps. This depletion region width overlaps. Now when no electron can flow, no electron can flow from, okay, these are totally overlapped. Okay. When VGS is equal to VP, when VGS is equal to VP, then the depletion region width, the depletion region width in the channel overlaps each other, then no electrons from source to drain can flow. No electrons from source to drain can flow and no current is produced. No current is produced. That is IDS is 0 when VGS is VP. Now the total drain current IDS is equal to IDSS 1 minus VGS by VP whole square. Now you can see when VGS is equal to VP. What happens when VGS is equal to VP? When VGS is equal to VP, what happens? When VGS is equal to VP, this 1 minus 1, 0. 1 minus 0, then the IDS current is 0. Okay, this is the region. This is the reason. Okay, students. Okay, students. This is about construction of n-channel Jfet. This is the construction of n-channel Jfet. This is an n-channel, the construction and how it is operated, what is the gate and drain, then source terminal channels, and how the channel length modulation occurs. Okay. Easy BTech guide for BTech and beyond. Thank you.